Welcome back into vector valued functions. Today we're going to talk about derivatives. Now, as you can see, with derivatives dealing all the way back in Calc 1, we have the definition of the derivative here. The limit as h goes to 0 of f of x plus h minus f of x over h. And it's very similar to what we have for vectors, right? Almost identical, except instead of f, we have r denoting a vector. And instead of the variable x over here, we're using t, right? But everything is the same. Right, we should have a visual over here as well. So remember, when we're solving for the derivative, it represents instantaneous rate of change, right? Or in other words, we're looking for the slope at that exact point, also known as the tangent, right? So we'll get into that later on, but you should see a visual of the actual tangent vector over here from our graph, right? So jumping into it, right? So the notation is, if I want to take the derivative with respect to t, and I'll go ahead and I'll use yellow here, it shows up a little bit better, of r of t, we'll go ahead and we'll put that there, of r of t, right, all we have to do, we'll put this as such, is we have to take the derivative with respect to t of each of our component functions, right? So essentially, if we know what we were doing in Calc 1, right, we should know what we're doing here. We're just doing 3 times as much work, right? And I've said that before with limits, right? Same idea. This is going to be g of t, comma, the derivative with respect to t of h of t. Right, so again, this d dt is just the derivative operator. It's an expression saying take the derivative with respect to t of f of t and so forth. Right, now, what I want us to remember is what is r of t, because eventually we're going to get into interpretation here, right? So what is r of t as far as, right, applications? R of t we represent using, or we talk about with the position function, right? Or the position vector, we'll say. Right, anybody? What is the derivative, right? So the derivative here, r prime of t, which is equal to v of t, right? What does v stand for? The velocity vector. And we have one more, right? If we're taking the second derivative. So remember what each of these also stand for as far as graphically, right? We're talking about instantaneous rate of change of the tangent vector. Or if we have a of t, or double r double prime, we'll get to a of t in a second, which is the derivative of the velocity vector, which is a of t, stands for acceleration, right? The acceleration vector. And I'll just write acceleration. Right, so rate of change, and we're over here, we're talking about the concavity. Right, but now we're dealing with vectors, so slightly different interpretation. And I think that's all we want to go over for now. While we do have some differentiation rules, and you'll see those pop up on the side over here. Right, so all the differentiation rules that we had in Calc 1, right, the easy power rule, e to the t, as well as product rule, chain rule, quotient rule, all of that we get here again for free, as well as some extra rules. You'll see them at the bottom of the rule differentiation rules down here. Right, so for now, we'll go into some examples in the next part of the video. But I will see you then. Let's go ahead and jump into some example problems. Right, so let's write down example 1. Now our first one is, again, we're just going to find the derivative of our position function here. And so we'll say r of t is equal to, and let's say we have e to the negative t, we'll say t minus t cubed, and our last one we will do the natural log of t. Okay? So as far as examples go and as far as derivatives, again, if we want to find the derivative of r of t, we just need to find the derivative of each individual component function. So we will just go down the line here, and let's say, well, what do we have? X, right? So x is equal to e to the negative t, right? So if I take my derivative with respect to t of e to the negative t, well, this is a slight chain rule, right? A very small chain rule that we have. The negative sign comes down in front, right? And we have negative e to the negative t. Easy enough, right? So we need to know to our e to the t rule, right? Plus a chain rule here. The next one we have is our y component. We have t minus t cubed, which means if we take the derivative with respect to t of t minus t cubed, these are some basic power rules, right? Derivative of t, 1 minus derivative of t cubed, another power rule, 3t squared. And lastly, right, we'll do one more, derivative of ln of t. And again, I know I'm overkilling it, and the next one will shortcut writing all this out, but just so we can see again, we're just taking the derivative of these component functions. So derivative with respect to t of natural log of t is equal to, well, natural log of t, 1 over t. Right, so we have all three of our different derivatives here. Let's go ahead, we'll put a squiggle over here. So we know that the derivative, or r prime, of t is equal to, well, what do we have? We have negative e to the negative t, 1 minus 3t squared, and 1 over t. Perfect. All right, so again, what is this telling us? Well, this could also denote, if we were doing an application, the velocity function. Here we're not thinking about applications yet, but we should be thinking about instantaneous rate of change, right? Or the tangent, right? What is tangent at a specific point? If I gave you a point, let's go ahead and do another one. Create a little bit of a line here. And we'll do example 2. Right, so example 2 will be very similar as far as the first part set up. I'm going to skip a couple steps this time though, so we don't write out everything. So let's say example 2, we have r of t is equal to, we're going to do 6t sine of t, comma, we'll do e to the t cosine of t, and the last one we'll just do e to the negative t again. All right, so let's pause for a second and examine what we have. We have a product rule here, right? A function times a function. We have a product rule here, it's a function times a function. And then we have this mini chain rule, just because of that negative sign there, right? It's going to come down. All right, so let's just jump straight to the derivative. I'll start from over here. So we'll say r prime of t is going to be equal to, let's do our first component, which is a product rule. So derivative of 6t, 6. Second one stays the same. And then we'll do plus, the 6t now stays the same, and you could have brought that 6 out to begin with. The second one, derivative of sine, goes to cosine of t, comma, same thing again, right? Another product rule, derivative of e to the t, well, that's e to the t, cosine stays the same, plus e to the t stays the same, derivative of cosine of t, well, that becomes a negative sine of t, comma, and our very last one, right, we've done this up here before, mini chain rule, negative e to the negative t. Okay, and it's very possible that in your problems that you may see, Of course, maybe we want to find the derivative of this vector function at a specific point, right? So let's say I give you some added information and I tell you, well, what is r prime or when t is equal to 0, right? So let's just evaluate it at 0. What do we get? Well, we know sine of 0 is going to be 0. We also know this is going to be 0, right? Let's just write everything out. 6 times sine of 0, well, that's 0. Plus 6 times 0 times anything is going to be 0. So our very first part is 0 plus 0. Very interesting. Our next thing is going to be e to the 0, which is 1, times cosine of 0, which is 1. So 1 plus e to the t, or e to the 0, is 1. Sine of 0, 0. And lastly, we have e to the 0 at the negative sign, so negative 1. So in short, our vector here becomes 0, 1, negative 1. Awesome. All right, we'll put a line under this. So again, as far as solving derivatives, if we're good with our rules from Calculus 1, right, we're just going to have 3 times as much work here. We did the derivative of each individual component function, mini chain rule, power rule, natural log rule, right? We need to know that one. We got to example 2, we picked it up a little bit. We did product function, same mini chain rule, right? We write it all out. And let's say I give you a point to evaluate it at, as easy as plugging in 0, and we have 0, 1, negative 1, right? So this is our rate of change, right, or our velocity vector at, right, 0. Okay, so hopefully this helps as far as going through derivatives. Again, break it up piece by piece. We're just doing 3 different derivatives for 3 different dimensions. I will see you in the next part of the video where we will talk about tangent vectors and unit tangent vectors. Essentially, we will be using these same examples here, but we're just going to add on one more piece. So I will see you there. Okay, welcome back. So in this part of the video, we're going to go through unit tangent vectors. Now, tangent just means we're taking the derivative. We end up with r prime of t. We've worked on taking the derivative in the previous part of the video, right? So we just really need to add the unit vector part. The definition should show up there. So let's jump into it. I'm going to use the same examples that we had in our previous video, or previous part of this video, right? So example 1, we had that r prime of t was equal to, we had negative e to the negative t. This came from a mini chain rule. We had the power rule, which left us with 1 minus 3t squared. And we had the natural log rule that ended us with 1 over t. And now what I want us to do is we're going to find the unit tangent vector at, let's go ahead and apply this to t. We'll write this over here. T is equal to, we'll do 1. Right, so we have r prime of 1 is going to be equal to, this leaves us with negative e to the negative 1, we do need to include that. We have 1 minus 3, negative 2, and we have 1 over 1. Okay, so this gets us our tangent vector. Now we need to turn this into a unit vector. Well, how do we do this, right? This is coming back from a couple of sections ago. We divide by its magnitude, right? And as the definition shows, we just need to divide by the magnitude. So let's write this over here on the side. We'll do a little bit of side work. We need the magnitude of r prime of 1. And what does that give us? Now, it's going to be an ugly number, I'm aware. Right? This is going to be the square root of, well, negative e to the negative 1. Negative times a negative, right? We're squaring it. So this becomes e to the negative 2 plus negative 2 squared. 4 plus 1 squared, 1, which means we're left with the nice square root of 5 plus e to the negative 2. Okay, right, so now we have our tangent vector. We have the length of that tangent vector. All we need to do now is combine the two ideas. And now normally you would distribute this to each piece of your component right? But I'm just going to leave it because this is ugly. So we'll say t of t, right, for the unit tangent vector is equal to, we'll write it as such. We have negative e to the negative 1, negative 2, positive 1, divided by the square root of 5 plus e to the negative 2. And we will leave that there, right? So normally you would distribute out this denominator to each component, but just for now, because it's ugly and I gave you an ugly example, we can leave it just like that, right? But the process remains the same. Even when you have a nicer problem, right? You find the derivative or the tangent vector, and then you're going to divide by its magnitude. Okay, so that was example 1. We're going to do one more using example 2, and I'll remind us of what we had for the derivative, right? Our derivative was a little bit longer because we had 2 product rules. So let's say example number 2, we had r prime of t was equal to, we did 6 sine of t plus, then we had 6t, right? We didn't take the derivative of this one. We took the derivative of sine. We ended up with cosine of t. Let's make this a vector, comma. The next part was another, right, product rule. So we had e to the t. And this was, we left it as cosine, right? So we took the derivative of e to the t, which is e to the t. We left cosine of t alone. And then we did the opposite, but it ends up being a minus sign. I'll explain why in case we forgot. Right, the derivative of cosine of t is negative sine of t. So that's where this minus sign is coming from. And finally, right, we had the mini chain rule. Okay? And now let's say we want to apply it at a specific function. So let's say t is equal to 0. We'll make it a nice and easy one. So t is equal to 0. What do we end up with? Well, this actually ends up being pretty nice, right? So we have r prime applied at 0 is equal to, well, 6 sine of 0, going to be 0. And I think we did this on the previous problem, but just so we don't forget. 0, 6 times 0, well, that's also going to be a 0. Right, e to the 0 is 1, cosine of 0 is 1, minus 0, and we have e to the 0 is going to be 1 times a minus sign, negative 1. So we end up with the vector 0, 1, negative 1, right? So we have our vector. This is a little bit nicer. And now what do we need? Well, we need to find, right, the magnitude in order to make this a unit tangent vector. So let's find the magnitude of r prime of 0, and it ends up being fairly straightforward, right? Ooh, stop that in its tracks. Had a little bit of a leak there. Okay. There we go. So we'll say this is going to be the square root of 0 squared, 0, plus 1 squared, 1, plus negative 1 squared, 1. We get root 2. Okay, now in this case, it did end up being a nice evaluation. So when we go to write our final answer, right, we'll say capital T, right, the unit tangent vector of t. We'll write it out fully. Well, this is going to be 0. This is going to be 1 over root 2. And I know there's the rule about not having radicals in the denominator for right now. Who cares? Negative 1 over root 2. And you can double check that that is indeed a unit vector. And we have our final answer, right? So again, same thing we did last time, right? We took the derivative, right? These are from our previous parts of our video. We apply a specific t value to make it a unit vector. We divide by its magnitude, right? And normally we would distribute it out to each piece. In this case, we left it as is. maybe it's a little bit better seen in our second example. All right, so that is it for derivatives. We will go through an example problem involving velocity and acceleration, but for right now, I will see you in the next part of the video. All right, last example for this video. And what we're going to do is if I give you some r of t, or some position function, so let's go ahead and write it down. R of t, right, it's going to be equal to root 6 t, comma, we'll do 3 e to the t, and we'll do e to the negative t, right? So if I give you some position function, I want us to be able to go to the velocity, to the acceleration, and to the last part that we need to introduce, which is the speed. Right, so in our case, if we're given the position function and we want to find velocity, right, so we'll write this here. You know what, let's use a different color. We'll go with the velocity function. Well, what is the velocity and compared to the position, right? We're just going to take the derivative. So in this case, right, the velocity, which is the derivative, so derivative of root 6t, we just leave the constant. Awesome. Derivative of 3e to the t stays 3e to the t. And lastly, e to the negative t, we do have this mini chain rule, as I call it, negative e to the negative t. Right, so that gives us our velocity function. Now the next thing we want to do, if we have our velocity function, is let's get down to acceleration. Right, so we'll do our acceleration function. And what is the relationship here? Right, well this is, I'll just write it out long form. Right, this is the derivative of the velocity, or the second derivative of the position function, right? So in this case, this is equal to, what do we have? Well, what is the derivative of a constant value? Unfortunately, 0. 3e to the t, very easy function because it does not change. And now our mini chain rule, we end up going back to positive e to the negative t. Right, so we did our first derivative, we did our second derivative. There's no difference. We're just taking the derivative of each one of these component functions. In this case, we get 0, 3 e to the t, and e to the negative t. Now we can see the visual over here. There is the blue vector, which represents the position function. The velocity is represented by the black vector, and I believe the acceleration function is represented by a dark maroon vector. Right, so if you're wondering what each one of those vectors are. And we still need our last piece, in which, what is speed? Right, so speed, ooh, I keep trying to use blue and it just doesn't work out. Speed is going to be equal to the magnitude of our velocity vector. So in this case, right, well, what do we have? Our velocity vector, right? We can still take the magnitude even though these are functions. It doesn't change anything. We're still squaring each component, right? So this is equal to the square root of root 6 squared, and so we'll do it piece by piece here. Squared plus, we have 3e to the t squared plus negative e to the negative t squared. And we can make it very, right, this is going to be a very easy simplification. So speed is going to be equal to the square root, that's not going away. Root 6 squared just becomes a 6. Let's see what we have here. This is going to be 9 e to the 2t. And lastly, we have negative negative, so plus e to the negative 2t. Okay, now I'm going to show some side work. This is a very acceptable answer here, right? That is totally fine. I'm about to do some side work over here. So we'll draw a line. If we wanted to do an algebraic simplification here to make it look a little bit nicer, what we can recognize is that we'll write it this way. 3, the square root of 3, let's say e to the t, minus, let's see if this works out, 3e to the t, correct, plus e to the negative t, there we go, squared, right? This is equivalent to each other, right? And you can double check 3e to the t squared, 9e to the 2t, this p squared, obviously e to the negative 2t, and also, right, if we do each individual piece, right, you'll find that you'll end up with this 6, right? You would have 3e to the t times an e to the negative t, that would give you a 3, you have 2 of those, you would get your 6, right? So this is actually equal to, if we wanted to break it down even more, 3e to the t plus e to the negative t. Now again, this first one, fine, acceptable answer. If you wanted to break it down even more, right, we can see that this is actually kind of like a perfect square, right? So we can go ahead and simplify and get rid of the square root and the square, and we end up with 3e to the t plus e to the negative t. All right, so that is our last example. In this one, we went from position, velocity, acceleration, but we can also go the opposite direction, and we'll see that in the next video when we go to integration. Hope you guys enjoyed the video. I will see you in the next one.